So today we're very pleased to have from UCLA, close journey, Stan Palasek, who will be talking to us on non-uniqueness and convex integration for the forced Euler equations. Thank you, Stan.
Thank you. Thanks very much, everyone, for coming, and thanks to Susan for inviting me. Really happy to come across town, and thanks for helping me get out of my jury duty today. It's just a bonus. So today I'll be talking about the Euler equations and convex integration techniques that I was working on jointly with Aynur Bulut, who's at LSU, and Huynh, who's at Georgia Tech. And so let me just introduce our system that we're considering. These are the incompressible Euler equations with a force. So there's some external force. So as usual, our unknowns are the velocity and the pressure. Well, so we're going to be interested in weak solutions of these Euler equations. It's easy to see that there is such a weak formulation if you multiply this by a test function and integrate both sides. You can come up with a formulation that works under quite minimal regularity. Let's say that our velocity field is L2 in space and time, and we can formulate weak solutions of this system.
No initial conditions.
Well, we can talk about solutions with or without. We will be looking at some with initial conditions, yeah. But in this area of turbulence and convex integration, it's pretty common to look at just solutions as objects in themselves, not necessarily part of the initial value problem. Yeah, so let me review the theory for classical solutions. So we assume our solution is let's say smooth. So it's well known that there exists a conservation of energy. So if we look at this kinetic energy at any point in time, basically it only changes if some work is being done by the force. So you should look at this in contrast with, say, the Navier-Stokes equations, where there's some dissipation which causes energy to be lost, kinetic energy to be lost. Also, for classical solutions, we have well-posedness theory. So that basically starts if you're just a little bit better than C1. So in this case of classical solutions, the initial value problem for Euler is unique, and the solutions are somehow rigid. So even in a weak topology, you can't approximate an arbitrary divergence-free vector field by a regular solution to Euler. So the solutions the problem has what you'd call rigidity. Let me talk about the motivation for why we would consider weak solutions to this equation. So in a rougher class than we had these properties on the previous slide. So in reality, we see that fluids have a tendency to cascade their energy to higher and higher frequencies, or to smaller and smaller spatial scales. Right? This is a familiar phenomenon. If you look at water that's moving in a fairly rough way, it creates little eddies and vortices, and within those eddies and vortices, they have their own little eddies and vortices if you wait for a while. So even if you start with a fluid where all the energy is sort of coarsely at coarse scales, it can send it to these smaller scales. That's just something we observe in real life. And there are a variety of sort of phenomena you expect to see in those types of fluids. One example is what they call anomalous dissipation. This is the idea that even though Euler is a conservative equation, so you have energy conservation, no energy is being dissipated here except by the force. A kind of incredible thing that has been observed in real experiments and simulations is that nonetheless, weak solutions can dissipate energy, even though it's supposed to be a conservative system. So that's quite surprising, and it's a consequence of the fact that energy can sort of run off to infinitely high frequencies and actually escape and disappear. That's called anomalous dissipation. There's also what you'd call instability leading to non-uniqueness. So if a sort of a very concrete manifestation of this is if you try to do the same fluid experiment twice, you're probably going to get totally different results if it's something very turbulent. Laminar fluids are much more stable and predictable, but the turbulent fluids, we expect to see this kind of breakdown of uniqueness. So a very important contribution was that of Onsager, who kind of looked at these turbulent cascades in Fourier space, and he did some semi-rigorous calculations and concluded that when it comes to anomalous dissipation, C 1/3, so the Holder space 1/3, it forms the threshold between conservation of energy and possible dissipation of energy. When you're looking at weak solutions, this is somehow the exact, even from the perspective of dimensional analysis, C 1/3 is sort of the right space where you start to see the failure of conservation of energy. The first rigorous proof came in 94 by Constantine and Titi, proving that if you have a solution of Euler which has greater than 1/3 Holder regularity, then it has to conserve energy. This is a fairly straightforward argument. Just looking at the normal way you would compute energy conservation, keeping track of the appropriate commutators and things due to the fact that you can't exactly integrate by parts if you have a vector field that's not continuously differentiable. It turns out 1/3 is exactly the regularity where you can prove conservation. Now Onsager also requires you to prove the other half of things. So if your solution is not C 1/3, you'd like to prove that it may not conserve energy. In some cases it might, but in general, it does not. So in terms of constructing wild and non-conservative weak solutions, the earliest example is by Scheffer, and later there was another example by Schnirelmann, who constructed non-conservative solutions that are in L2. So no continuity of any type, just finite energy. There was a subsequent construction I didn't put in here by Schnirelmann of a well, actually no, they only produced L2 solutions. Deleuze and Zeklahidi came along and revolutionized this problem of constructing turbulent solutions to fluid equations. They brought in a technique called convex integration, which was originally invented by John Nash for problems in geometry related to asymmetric embedding. And they applied it. They showed that it just as well as it works for isometric embedding, it works for fluid equations. And they used it to construct bounded solutions. In fact, they constructed solutions that are compactly supported in space and time. So basically you have a fluid that starts off completely still and just out of nowhere does something absolutely wild. In fact, I think the solutions they constructed had length 1 for the velocity field everywhere where they were supported, and then just die off out of nothing. So that's, justifies the common term wild for these solutions. It's nothing like you would see in nature. But notice it does fail to obey conservation of energy. Subsequently, Deleuze and Zeklahidi were able to refine their construction in 2013. They created continuous solutions, and then they later were able to go even further and construct Holder continuous weak solutions, just something like 1/10 Holder regularity at first. And I'll talk later about how one would do this. And there were many subsequent papers by Deleuze and Zeklahidi, as well as other authors, Buckmaster, Denary, Ised, and others, to incrementally get more and more regularity for these wild solutions to the Euler equations. So the culmination of all of this work was by Phil Ised in 2016. He finally resolved the conjecture of Onsager and produced solutions to Euler that do not conserve energy, all the way up to, but not including the C 1/3 threshold. So this resolves Onsager's conjecture, showing that 1/3 is exactly the regularity cutoff for conservation.
So 1/3 itself is included in the conservation.
1/3 itself is still open, and that would be very nice to know, because you kind of expect that exactly 1/3 it should really be realized by fluids, but the techniques that we use unfortunately just barely fail to work. ISET was able to construct solutions in a later paper that are in every single Holder space below 1/3 at the same time, but not in 1/3 itself. Although they do approach Holder 1/3 as you look at smaller and smaller scales. So the endpoint is still open, and that would be very nice to be able to resolve. So the main technique for all of those constructions, not including the very, very early ones in the 90s, is this technique that's due to John Nash and was made more systematic by Gromov. It was originally used by Nash, like I said, in isometric embedding, and Gromov refined it for all other kinds of problems in geometry. The idea is that there's something called the H principle. If you have a solution, if you have a problem that you can kind of construct what they call formal solutions of, then at a low enough regularity, you can often sort of add very rough perturbations to it and make it converge in some weak sense to a true solution. And that's the philosophy that we use in fluids. So we somehow have to relax the problem. And then if you look at a low enough regularity, you show that solutions are actually somehow dense in the space of all possible solutions in a weak topology. So in the case of the Euler equations, let me just summarize the state of the art of what we know. So these are the properties I stated at the beginning of what we know are true for classical solutions. So classical solutions we know conserve energy. They're unique and they have this rigidity property. So ISET, like I mentioned, resolve the energy conservation. So we know that there's no conservation below 1/3 and there's always conservation above 1/3. Uniqueness is not yet resolved. So ISET's proof implies non-uniqueness of the initial value problem. So you could have two solutions that have the same data yet are not the same for all time. And this follows from ISET's work actually as well, because deconstruct solutions that are compactly supported in time. So in particular, they at the initial time, they can agree with this identically zero solution, a solution that's not moving at all, and then they diverge for a while and then they come back together. So that certainly breaks uniqueness of the initial value problem. However, between the 1/3 regularity and the C1 threshold, that's entirely open. For the just unforced Euler equations, we have no idea what happens between 1/3 and 1. And then the other interesting question is rigidity. This connects to the H principle I mentioned. As you would like to know if something is true along the lines of, if I give you any divergence-free smooth vector field, can you necessarily approximate it in some weak topology by weak solutions of the Euler equations? So it was shown in sort of an extension of ISET's work by Buckmaster, Delellis, Sepulveda, and Vicol, that up to the C1/3 regularity, you actually do have this, what they call H principle. Although it's so between 1/3 and 1, the rigidity as well is completely open. So this is the state of the art for the unforced Euler equations. If you go to 2D, so everything I've mentioned so far is 3D, which is kind of the most physically relevant case. 2D we care about as well. If you think about the atmosphere, that it's an approximately two-dimensional fluid in the sense that the length scale of the Earth is much larger than the length scale of the thickness of the atmosphere. So 2D fluids are of interest as well. And in this case, we have sort of less room to use these techniques, as I mentioned in the talk. And so the negative results, so this column, are actually true only up to 1/5. So there's an even wider open range in these cases in the 2D problem. So the goal of the methods I'll talk about in this talk is to close, especially this gap, and also try to close the gap in 2 dimensions as well. Okay, so let me mention some important work that is a totally different approach to convex integration. This is a remarkable development by Misha Vishik fairly recently, and he not using convex integration, he was able to find a 2-dimensional vortex which is unstable. So it has an unstable eigenvalue, and he used that to he basically looked at this vortex in self-similar coordinates and was able to use this instability to create a second solution that starts from the same initial value in the sense of these. Well, I won't go into too much detail, but in the sense of these self-similar coordinates, he's able to make it so these two solutions have the same data and diverge from each other. He had to introduce a force as sort of a cheat, which we accept, and I'll do the same in this talk. But basically, it led to non-uniqueness in basically what should be the sharp spaces. So his solution, well, the best property is that its vorticity, which is the curl of velocity, is in any LP for p less than infinity. And by basically Maury's inequality, this implies that the velocity could be in any C alpha for alpha less than 1. Now, these are similar to how I explained it before. These are basically the sharp spaces. So as I mentioned, C1 corresponds to where if we're just a little bit better than C1, we have local opposedness for Euler. So having C alpha for alpha less than 1 is as good as you can get. And having vorticity bounded in LP is essentially sharp too, because there's a classical theorem of Udovich that says that if vorticity is in L infinity, or even if it's in LPs and the P's the LP norm does not increase too fast as P goes to infinity, then you have uniqueness of the initial value problem. So Vishek's vortices can be made to be in any LP for P less than infinity. So showing that these criteria are essentially sharp for 2D Euler. Of course, if you show non-uniqueness for 2D Euler, you also have non-uniqueness for 3D Euler, because you could take any 2D solution and essentially just make it not depend on the third spatial dimension. So when you're proving negative results in fluids, typically, if you prove it in a low dimension, it implies it for the higher dimensions too. So in the case of the forced Euler equations, Vishek essentially resolved the question of uniqueness, and he got the best possible result. And I should mention that there's another impressive development by Albert Bruy and Colombo. They use this result to prove non-uniqueness of the Navier-Stokes initial value problem in basically any supercritical space, by showing how you could take this and introduce a viscosity and extend it to 3 dimensions. So just a side, that doesn't apply for the Euler equations. So Vishek's result is very impressive. It's in all the sharp spaces, but what I like to remark is it's a very narrow non-uniqueness scenario. It only applies to this specific family of vortices. It doesn't tell you what happens for generic data. So it would be nice, and something that convex integration tends to give you is it tells you what happens more typically. You can often make a statement for all data or for a dense set of data or something like this. Yeah, being able to prove something similar using convex integration results would tell us something about what happens commonly. So indeed, this is what we're going to try to do. And so I ask, is convex integration possible above the Onsager regularity, meaning the regularity C1/3, which has been the sort of barrier for the Euler equations so far. Now, it is clear that energy conservation is an obstruction for convex integration techniques. Convex integration involves adding this sort of high frequency perturbation, and you're usually free to sort of choose a profile for these perturbations. And thus you can tweak, it's pretty clear you can tweak the energy profile of your solution. So the fact that solutions to Euler have to conserve energy above C1/3 seems like a serious obstruction to using convex integration. And indeed it is, but we relax the problem to make it so energy conservation is less of a strict constraint. And so in particular, we add a force analogous to what Vishek does, although we use it for a very different purpose. So our main theorem is as follows. You can pick any 3 divergence-free vector fields that, let's say, they're smooth, and any exponent that's less than 1/2. And this construction will give you 2 velocity fields which have the same data, but you can pick the value of them at time 1. So you can control these velocities, and it gives you a force. And so these U and V both solve Euler with the same force. So in other words, we can from any data we can give you non-uniqueness but we have to prescribe the force. And so these solutions are above the Onsager threshold in the sense that they do conserve the energy balance. And we prove that when the velocity fields have at least this much regularity, and the force has at least this much regularity, then the solution must obey the energy balance in the sense that the work done by the force balances any change in the kinetic energy. And in fact, we can say something a little stronger as follows, which is that we can target the force up to a small error. So if you give any data and any smooth, so I'm calling capital F sort of the potential for the force. So the entire force is the divergence of F. Let me just maybe I'd write that to make it clear. So we're considering Euler. So your entire force is the divergence of some potential. This would be a 3x3 matrix. This just kind of algebraically works with the way convex integration is set up. So keep in mind that the entire force is more like the derivative of this capital F. So what this is saying is that for any initial data, we can produce two solutions with the same data and the same force, and moreover, the force can be chosen to be close to the desired force. Of course, the topology in which it's close is somewhat weak because the actual force is the derivative of this capital F. So we're roughly speaking saying that the force is dense in some somewhat negative order Bessel space. So in particular, you could pick the force to be arbitrarily small in this norm, but unfortunately, we cannot say anything about the unforced system. Our method relies on the existence of a force. But the main thing to note is that this is for any alpha less than 1/2. So we're exceeding the 1/3 threshold that's been the ceiling up to this point. And this leads us to the following conjecture, which we certainly leave open, but there's a hint of it. So this is now the chart for the force system. So negative results are strictly easier to prove for the force system than in the chart I showed you before. So the first line is essentially the same. The second line for uniqueness, well, so Vishek, as I mentioned, provided an example of non-uniqueness for the force system all the way up to C1. So for the force system, uniqueness is resolved. The question is about rigidity, whether you can approximate any smooth vector field by solutions to Euler. And well, for several reasons, we, as a result of this work, conjecture that 1/2 is the threshold for rigidity for the force system. Now there are a few reservations that we have about this. First of all, it's not entirely clear how to formulate a precise H principle for the force system, because, well, is the force allowed to be part of the approximation that we are considering when we're saying that something is rigid or not? It's a little bit unclear, but there has been some precedent for 1/2 being a threshold, which is a motivating factor. So recently, C1/2 has been established as the exact threshold for some problems related to isometric embedding and isometric extension. This is work of Delellis, Inouin, and Cao. They've shown that for the original type of problem that led to convex integration being invented, C1/2 is the threshold. So they've constructed H principle for regularity below 1/2, and they've shown rigidity above 1/2 for these problems. So given the fact that our convex integration also gets stuck at 1/2, this motivates one to expect that perhaps 1/2 is also the threshold for 3D Euler. Yeah, so we leave that as a question for now. So let's get to the strategy of convex integration. So this basic outline I'll give is due to Delison's equidity for the Euler equations. The idea is you construct your weak solution V as a strong limit of solutions which are supported in some frequency band, a frequency ball. So we relax the Euler equation and we basically by adding this error on the right-hand side. So R is going to be some small rank 2 matrix. And the goal is to perturb V over and over again to try to get this matrix get smaller and smaller. So the entire right-hand side is not small, let's say in C0, but R will be small in C0. And so this will make this as a weak solution, or I should say converge to a weak solution to Euler. So we say that the velocity field and the error, which we call a Reynolds stress, is supported at frequencies up to some large frequency lambda, and that the amplitude of the Reynolds stress is going to 0, and we call that amplitude delta Q plus 1. So Q here refers to the steps of this iterative process. So this equation corresponds to this current state of our iteration at the Qth step, and then we proceed to Q plus 1 and Q plus 2, and then as Q goes to infinity, we hope to achieve our desired weak solution to Euler. So the basic idea is that we construct the next velocity in the sequence by adding a perturbation, which we'll call WQ plus 1. And WQ plus 1 has its frequency supported in a higher frequency band. So you could think that VQ and RQ have their, if this is frequency space, so R3 is frequency space, VQ and RQ have their frequencies supported in a ball of radius lambda q. And then you define the perturbation, WQ plus 1, to be supported in a much larger frequency band of frequency lambda q plus 1, which is much larger than lambda q. So you're adding this lacunary sequence of perturbations, lacunary frequency space. So this sequence of lambda q's is increasing at some double exponential rate. And the main goal of this perturbation is to cancel out RQ. So the idea is to carefully design WQ plus 1 to cancel out the error. And you can kind of already see how that's going to happen, because if you imagine adding this high frequency perturbation to V, there's going to be a nonlinear interaction when the W interacts with itself inside of the divergence. And the goal is to get that to cancel with the error. So hopefully that's just the basic philosophy. Hopefully that makes sense.
So what about this BQ times WQ plus 1?
That's a good question. Yeah, well, I'll get to that. Yeah, that you're right. That's the main difficulty that gets you stuck at 1/3 is some of those interactions between V and W. So yeah, I'll explain those in further detail. Okay, so as someone wisely pointed out, there are these other interactions that we have to worry about. There's the interaction of W with itself, and then you have to worry about the places where W hits V and V hits W. So all I did here was I replaced V by V plus the perturbation. So the goal basically is to get this to cancel and then to make these other error terms somehow manageable. And the way in which they're manageable is they have to fit into the divergence of a new error. So we have to define a new error that's going to be able to absorb all of these error terms that have been created when we perturb VQ. And we, of course, want to make it much smaller, specifically smaller in the C0 norm. So when this subscript 0, I just mean the C0 norm. We want to make it smaller than the previous error RQ. Okay, so like I said, we want this nonlinear interaction to cancel the previous one. So recall that I said delta Q plus 1 is the amplitude of RQ. So therefore, the amplitude of WQ plus 1, since its square needs to cancel out the Reynolds stress, it should be the square root. Moreover, like I said, WQ plus 1 has this large frequency lambda Q plus 1. So with these two pieces of information, we can estimate the Holder norm of this perturbation. We know the frequency and we know the amplitude. So its Holder norm roughly should be on this order of magnitude. And we want this to go to 0. And that leads us to a relationship between delta and lambda. Because if we need this to go to 0, then basically we need a relation like this. Of course, you could say that, well, we actually need this to be much less than the right-hand side, but basically all the parameters are increasing or decreasing really, really fast. So the difference between being comparable and being summable is essentially negligible. So as a rough approximation, I'll just write this relation. Okay, so let me explain the main new approach that we created that is supposed to allow us to go above the 1/3 threshold. So just for your convenience, I wrote out all the error terms again. So we have what I'll call the linear errors, which are where our perturbation interacts with the previous velocity field. So these two errors, and then the quadratic error where the perturbation interacts with itself, which is supposed to cancel the R. And all of it needs to go into this kind of error trash can, which is RQ plus 1. And okay, because of the Euler equations, there's some pressure, which we're not too worried about. Essentially, this pressure is just a projection onto divergence-free vector fields, so we don't worry too much about that. And what you find is that using what I've described, if you arrange things properly, as I'll show, the quadratic interactions are acceptable all the way up to regularity 1/2. What leads to issues are the linear errors, and this is what gets you stuck at 1/3. So for example, there's this error with WQ plus 1 differentiating the prior velocity field. You want to get it into RQ plus 1, so you have to invert this divergence. So that's why I wrote this inverse divergence here. And basically you end up finding that it has this size, as I'll explain. And in order to make this small enough, in order for it to be smaller than the next delta, you end up finding that this requires beta to be less than 1/3. So you get stuck at 1/3, and this is essentially the reason why the Onsager conjecture gets stuck at 1/3, as it should, because we have a positive result saying you can't have energy conservation above 1/3. Okay, so how do we get around this? So we introduce something that we call alternating convex integration. So instead of just looking at one equation, you look at equations for both of the velocity fields. So these will, U and V, we want to both be solutions. Oh yeah, go ahead.
What's the initial condition on W?
We don't worry too much about the initial conditions. But basically what happens is, maybe imagine we have these U and V's. And we want them to be equal initially, and we want them to diverge from each other. So our perturbations are essentially localized in time. So as long as we keep them pretty localized in time, we can just kind of work on each time interval independently. So we don't as much think about this as an initial value problem. Okay, yeah. So the idea is to consider these two equations in parallel. So to look at the equation for U and the equation for V. So we want them to have the same force. We want them to have the same data, which I didn't write here, but that is something we're insisting. But this error that people call the Reynolds stress, we only put on one of the two equations. So that's the key idea. So the idea is that one tries to arrange things so that
FQ here, I missed.
Oh, this is just this is going to be the force. So I'm writing the force as the divergence of some potential.
Why does it depend on Q?
It will change from one step to the next. So the final equation that we have will be this. So the FQs will converge to the final force.
I see. Just like the UQ, just like the VQ.
Exactly. Yeah. So it's going to change throughout the iteration, but it'll converge in this Holder space. Yeah. So the goal is to arrange things so that U and V are only perturbed on alternating steps. So let's say on the odd steps you perturb U, and on the even steps you perturb V. the goal is to modify the force at each step so you can move the Reynolds stress between the two systems. So let's say we have this to start. Let's say we're at step Q and we have a system that looks like this. The idea is we use sort of conventional convex integration methods to perturb V to correct this Reynolds stress here. So we're perturbing V to cancel out this. So that procedure, which I haven't described in detail yet, but let's just say we can do it, causes us to update V and update R. So now R is smaller. And then we modify the force. So we define the new force to be the old force plus this Reynolds stress. And that allows us to essentially move this error onto the U system. So now the error has been moved. And now, well, you perturb U to cancel out the stress that appears here. So on alternating steps, you perturb alternating U's and V's. What that leads to is essentially since you're only perturbing V on every other step, the frequency of V is smaller than it is for the normal convex integration because you essentially skipped the previous perturbation for that V. And that improvement on the C1 norm of V leads to ultimately the improvement of the regularity of the solution. Basically what you're doing is you're making the sequence of frequencies more lacunary. The key way that you create the new Reynolds stress, as I'll describe, is by performing sort of a stationary phase argument in order to invert the divergence. So the more spread out the frequencies are, the more powerful those stationary phase ideas are.
So what is keeping you from spreading out more?
It's just the regularity itself. Because recall that if you look at the velocity in some C beta, that's like so the faster the lambdas increase, essentially the worse the C beta norms are, because you lose this lambda factor every time. So yeah, the trade-off normally is that you want to make these lambdas as close together as possible in order to make this work well. I could be more specific. So specifically, we usually take lambda Q to be A to the B to the Q. So it's this double exponential thing. And with the typical convex integration scheme, you have to take, sorry, I'm running out of space. You have to take beta to be less than 1/1 plus 2b. So in order for this sequence to be increasing, you need b to be bigger than 1. So the smaller you take b, the closer you can get beta to be 1/2. But so that's one side of the trade-off. The other side of the trade-off is the larger you take b, the stronger the stationary phase argument is that I'll explain shortly. So by doing this perturbation on every other step, we get that extra spreading out for free without having to make the regularity worse. Yeah, I'll show some of the parameters in a bit if we have enough time. Yeah, so just a note, since the force is coming from transferring the Reynolds stress back and forth between the equations, the force essentially has the same regularity as the Reynolds stress. The Reynolds stress is like the square of the perturbation. So since the perturbation has amplitude of this delta to the 1/2, well, you essentially get that it has twice the Holder regularity as the solution. So capital F is in C2 beta. So when we differentiate it to get the actual force, it's 2 beta minus 1. So it's just barely fails to be continuous in the sense that at frequency lambda, it has amplitude like lambda to the epsilon. So maybe I should say it's just barely not bounded. We can make it as close to bounded as you like. So that's the regularity of the force. Okay, so let me share some of the details for how this scheme works. So the one of the important errors is this, which people often call the oscillation error. So this is the term where we want this to cancel the Reynolds stress. Now, clearly we can't get this as an identity. We can't make this identically 0. because W lives in this very high frequency band, and the Reynolds stress lives in this small frequency area. So there's no way we can get this cancellation to be exact. But the goal is to get the high to low interaction of the W hitting the W to hit the Reynolds stress. So more specifically, what we just as an ansatz, let's take our perturbation to be some low frequency function times a high frequency function. And specifically, we take this high frequency part to be a shear flow, meaning that the direction that the vector field is pointing is perpendicular to the direction in which it's oscillating. So this type of shear flow trivially satisfies the Euler equations because you could just imagine a fluid where it's pointing in a direction where it's not changing. So the fluid is just happily gliding past itself. So that's in a high frequency domain, and then A could be essentially arbitrary. We more or less get to choose A as we like. So you should think of this as a slow function and this as the fast function. Okay, so as I mentioned, because we've chosen this special shear flow form, when you take the fast divergence of this, you get 0. When you take the entire product and you take the divergence, so basically let us subtract off the average of phi squared. That's why I'm saying the average of phi squared is 1. So we can sort of decompose this as the divergence of a squared times this constant tensor, and then the part where the divergence hits the a, specifically the a squared, and then you're left with this. So the point is, since we chose phi squared to have average 1, this is a function which oscillates very fast but has 0 average. So you could think of it like e to the I lambda x. So it's a very fast oscillating 0 average function. Okay, and the beautiful idea that's originally due to Nash is that, well, if you take, this alone cannot cancel out R. This is just a rank 1 matrix. Obviously, it cannot cancel out an arbitrary symmetric tensor. However, if you take several of these rank 1 tensors, it can fully cancel out an arbitrary matrix. And this is the key lemma that's the basis of many kinds of convex integration proofs. If you give me an arbitrary positive definite symmetric matrix, then you can write it as a positive linear combination of rank 1 matrices. It's just some finite number. And moreover, you can, as long as you choose your tensor to be away from 0, you can make it so that these coefficients vary smoothly as a function of the tensor. So this is a decomposition that Nash already was using back in his isometric embedding proofs. So by writing a combination of these things, we can choose things that are going to cancel out R. So specifically, we update our ansatz as a sum of these pieces, like we were considering before, in such a way that these phis are disjointly supported. So in 3 dimensions, this is not really a problem. We use what people call Mikado flows, which are basically shear flows that are concentrated in a pipe. So they're supported inside of a pipe, and then you can choose some of these that point in different directions. So you could have a pipe pointing in one direction and then a pipe pointing in another direction that's disjoint. And you can take as many of these as you need, which is only 3 or so. No, that's in 2D. You need a few more in 3D. But the point is you can take any finite number of disjoint pipes pointing in different directions as you need in order to generate all of the symmetric 3x3 matrices. Positive definite matrices. So you write your full perturbation as a sum of these things. I'm leaving out some key details, actually. You need to write this in Lagrangian coordinates in order to deal with one of the other error terms that involve the material derivative, but for the sake of simplicity, I will omit those technicalities. So putting this all together, you get this part, which you can construct the coefficients using that lemma from the previous slide to exactly cancel the Reynolds stress. And then this part is very nice because your derivative is only hitting these slow coefficients. The fast part is not being differentiated because we chose this to be a shear flow that exactly solves the Euler equations. So the first term vanishes exactly. How do we deal with the second term? Well, in order to fit it into the next error term in our iteration, we need it to be the divergence of some small tensor. The tensor will of course be high frequency, but we want it to be small amplitude, smaller than delta q plus 2, if you remember the name of the parameters. Now again, like I said, the derivative is only hitting these slow coefficients, which is good news. If it was hitting this fast part that oscillates at the high frequency lambda q plus 1, we would be in big trouble because we'd lose a factor of lambda q plus 1. So I'll skip the numerics in the interest of the numerical aspects in the interest of time. Just to say that, well, this part is, like I mentioned, has zero average and it's oscillating very fast. So if you integrate this thing, which lives in this high frequency band, if you invert the divergence, you're going to gain a factor of 1 over that high frequency. It's like if you integrate a sine of lambda x on the torus, you get something of size 1 over lambda because you're integrating something that's very fast. And so you end up with this very helpful factor of 1 over lambda q plus 1. So this error term as a result will have this size. And well, your goal is to get this to be smaller than the next small size for R, which is delta q plus 2. And you find that you can do this. I already wrote some of these scales before. You find that you can do this when beta is smaller than 1 over 2b, again, using this description that I used here. And by taking b arbitrarily close to 1, you can get beta to be up to 1/2. So it turns out that for this quadratic interaction error, everything is okay up to 1/2. Unfortunately, for the linear terms, things are not so smooth. So I'm going to focus on this term, which people call the Nash error, because it did appear in Nash's proof of the isometric embedding theorem, a similar error term. So how do we deal with this term? Well, okay, I won't spend too much time on the parameter sizes, but basically we know the amplitude and we know the frequency. So if we want to fit this error into the divergence of something small, hopefully, it should look like this. So we know the amplitude of W is this. We know the size of the derivative of the previous velocity field is basically this big. By the same argument, this whole error term is concentrated in this high frequency band. So when we invert the divergence, we pick up 1 over this lambda factor, which again makes this whole thing very small. And well, indeed, we can make this smaller than the next small delta as long, like I wrote before, as beta is smaller than 1 over 2b plus 1. And then taking b to be as small as we like, we can make beta to be as close to 1/3 as we like. So this is what blocks us at 1/3, but it also shows why the alternating scheme works all the way up to 1/2. Again, I'm sort of sliding under the rug how to deal with this term because it adds lots of complications. So let me just mention, we're getting to the last part. The point of the alternating scheme now is that since we didn't do convex integration on V on the previous step, we did convex integration on the other velocity field. This VQ in the C1 norm is a whole step in the iteration smaller. So that gives us an improvement of these bounds, and it leads to better estimates for these linear terms. And I'll spare you the computational details, but hopefully that makes sense. So basically, we're making these frequencies more lacunary, and therefore the C1 norms are not increasing as badly, which leads to this improved estimate. Let me mention the similar improvement works for 2D Euler, where I said before, the scheme as it's presented here only works up to 1/5. I won't go into the details why. It involves sort of a technical clash between ways that you deal with the transport error and ways that you deal with the quadratic error. But basically, for very annoying reasons, you have to choose a time scale that obeys both of these inequalities at once. Using the typical scheme, if you take based on the size of this, you get beta stuck at 1/5. Using the improvements from the alternating scheme, you get a similar improvement, and actually you can get up to 1/3. So the point being that this alternating scheme has applications to other problems in fluids where the current techniques are somewhat limited. So that's 2D Euler. So let me just finish up by mentioning some future directions. Like I mentioned earlier, the C1/2 threshold for flexibility is conjectured and still open, so it'd be very interesting to understand that. You can apply it to other PDEs. I mentioned 2D Euler. SQG is a work in progress. Very recently, just this month, some work of Mimi Dai and her student Khang appeared using similar ideas as ours to deal with stationary SQG and slightly improve the regularity available there for stationary solutions of SQG. Surface quasi-geostrophic flow, should define my abbreviations. Another question, which is very hard, we have no suggestion how to do it, but it would be very nice if you could remove the force entirely. Our method just lets you take the force to be arbitrarily small. And finally, let me point out that one could hope that one might be able to prove an Onsager theorem for the forced version of Euler or SQG above specifically 2D Euler, where the Onsager threshold is still an open problem, whether it's 1/5 or 1/3 or somewhere in between. It's possible that one could use a similar alternating scheme to find solutions that break the forced energy balance. That would be interesting as well. So with that, I will wrap up and thank you for your attention.